For centuries we lived in a predictable universe. Isaac Newton's laws of motion and gravity explained the movements of planets and stars. They explained the tides. They explained why apples fell from trees. It was a clockwork universe. Everything moved with precision. Everything was predictable. James Clerk Maxwell added to this elegant picture. He described the interplay of electricity and magnetism. His equations predicted the existence of electromagnetic waves. These waves, we now know, include radio waves, visible light and X-rays. The universe seemed to be an open book. We thought we were on the verge of understanding all its secrets. But the universe, it turns out, had other plans. As scientists probed deeper, they stumbled upon mysteries. Some observations simply couldn't be explained by the laws of classical physics. One such mystery was the photoelectric effect. Light shining on certain metals could dislodge electrons. But only light above a certain frequency, regardless of its intensity, could do this. This defied classical physics, which said that the energy of light should depend on its intensity, not its frequency. Another puzzle was blackbody radiation. A blackbody is an object that absorbs all radiation falling on it. Classical physics predicted that such an object would emit an infinite amount of energy at high frequencies. This was clearly absurd and became known as the ultraviolet catastrophe. The universe, it seemed, was not as neat and tidy as we thought. These mysteries signaled the birth of a new physics. It was a physics that operated on the scale of atoms and subatomic particles. It was a physics that defied common sense and intuition. This new physics came to be known as quantum mechanics. In 1900, Max Planck proposed that energy was not continuous, but came in discrete packets, which he called quanta. This revolutionary idea explained blackbody radiation. It laid the foundation for quantum mechanics. 5 years later, Albert Einstein used Planck's idea to explain the photoelectric effect. He proposed that light itself was quantized, existing as particles called photons. The quantum revolution gained momentum. Niels Bohr proposed a model of the atom where electrons could only occupy specific energy levels. He explained the spectrum of light emitted by atoms. Werner Heisenberg introduced his famous uncertainty principle in 1927. This principle states that we cannot know both the position and momentum of a particle with perfect accuracy. The more precisely we know one, the less we know about the other. This wasn't just a limitation of our measuring instruments, it was a fundamental property of nature. The universe, at its core, was uncertain. This idea was deeply unsettling to many physicists, including Einstein, who famously said, "God does not play dice." Section 5. The Copenhagen interpretation. The strangeness of quantum mechanics didn't end there. The Copenhagen interpretation, developed primarily by Bohr and Heisenberg, offered a bizarre explanation for the behavior of quantum systems. According to this interpretation, particles don't have definite properties until they are measured. The act of observation somehow forces the particle to choose a particular state. This interpretation also introduced the concept of wave-particle duality. Light, which we normally think of as a wave, could also behave like a particle, and electrons, which we typically imagine as particles, could exhibit wave-like properties. The universe was becoming increasingly difficult to pin down. Einstein's skepticism. Einstein, despite his pivotal role in the development of quantum theory, remained deeply skeptical of the Copenhagen interpretation. He believed that quantum mechanics, while successful in explaining experimental results, was incomplete. He dedicated much of his later life to searching for a deeper theory that would restore determinism to physics. Together with Boris Podolsky and Nathan Rosen, Einstein proposed a thought experiment in 1935 that became known as the EPR paradox. This thought experiment involved two entangled particles that were linked in such a way that measuring the state of one instantaneously determined the state of the other, regardless of the distance between them. Schrödinger's cat. Einstein saw this as evidence that quantum mechanics was missing something. He believed that the particles must possess some hidden variables that determined their properties beforehand. Erwin Schrödinger, another giant of quantum mechanics, also had doubts about the Copenhagen interpretation. He devised his own thought experiment, now famous as Schrödinger's cat. In this thought experiment, a cat is placed in a box with a device that has a 50% chance of killing the cat. Until the box is opened, the cat is considered to be both alive and dead, according to the Copenhagen interpretation. Schrödinger found this idea absurd. He, like Einstein, believed that there must be a more complete explanation. The triumph of quantum mechanics. Despite these objections, quantum mechanics proved to be incredibly successful. It accurately predicted the outcomes of countless experiments. It became the foundation for many branches of modern physics, including particle physics, nuclear physics, and condensed matter physics. The debate between Einstein and Bohr about the completeness of quantum mechanics continued for decades. It remains one of the most fascinating and profound debates in the history of science. While Einstein's dream of a deterministic theory has not been realized, his challenges help to solidify and refine our understanding of quantum mechanics. Quantum technology. Quantum mechanics is not just an abstract theory. It has had a profound impact on our technological world. The transistors that power our computers and smartphones, the lasers used in telecommunications and barcode scanners, the medical imaging techniques like MRI and PET scans, all of these technologies rely on the principles of quantum mechanics. Quantum mechanics is also paving the way for new technologies. Quantum computers, still in their early stages of development, have the potential to revolutionize fields such as medicine, materials, science, and artificial intelligence. The future of physics. The journey into the quantum world has been a profound one. It has challenged our understanding of reality and forced us to confront the limits of our intuition. While quantum mechanics has been incredibly successful, many mysteries remain. What is the nature of entanglement? Is there a deeper theory that unifies quantum mechanics with general relativity? Can we build large-scale quantum computers? The answers to these questions will undoubtedly lead to new revolutions in our understanding of the universe. The quest to unravel the secrets of the quantum world continues, and it is a quest that promises to be as exciting as it is challenging.
If you enjoy this channel, don't forget to hit that follow button. Your support drives my creativity, and together, we explore the wonders of science. Let's make discoveries together.